Friction is a resistive force that acts against motion. In this picture here, we have a little kid. This little kid is applying a force to the couch there, but the couch isn't moving. That means there must be some other force acting backwards, canceling out the supplied force to keep the acceleration of the couch equal to 0. And that force that we have is the force of friction. It's a resistive force, meaning it resists any motion. We're going to see two different types of forces, frictional forces. Static friction holds a stationary object in place, right? See, static has the same root as stationary. And since we have so many different forces that all have F's, I use a kind of scripted F to represent the special type of frictional force. And I have a subscript S there for static friction. If we have to have an object that's already in motion, then we have kinetic friction acting on that object. Kinetic means in motion, right? It's the same root as kinematics, which is our study of motion we've been doing up to this point. The same scripted F for friction, and I have a subscript K for kinetic friction acting on a moving object. The kinetic friction is what slows down a moving object and brings it to a halt. We can look at a case study here to understand what's going on with friction. Here we have a system where we have a box that's sitting on the floor. You apply a horizontal force to the box, but the box does not move. So let's start by drawing a picture. We're told that we are applying a force, that would be a tension force that we're applying with a rope, but the box does not move, meaning that our acceleration is 0. And so we want to understand what's going on here. Well, if we're talking about forces and motion, the way that we put those together is by using Newton's laws. In this case, we can see that the acceleration is 0 because the box is not moving. And so if we're applying a tension force of 75 newtons, but the box is not moving, this tells us that the net force would have to be 0. That's Newton's first law. Then there has to be something else canceling out our 75 newtons, and we can conclude that there must be a static frictional force whose magnitude is 75 newtons acting in the opposite direction to cancel out our applied force. So static friction would have to be 75 newtons in this case to cancel out the tension, to give us what we're observing in the system. So we can expand on that idea. We know the static friction was 75 newtons in the previous case because it was acting to hold the block in place. It was canceling out whatever force we were applying. So we can imagine if we apply a little bit of force to an object, we get a little bit of static friction as a result. Whatever force we do apply, the force of static friction will be equal in magnitude and opposite in direction to hold the object in place. If we push harder, then we would have more static friction. If the object is still not moving, we could push harder still, and the object still wouldn't move. But you can imagine eventually with any object, right? If you get, a big enough tractor or a big enough truck, you could drag any object and get it to move eventually. So there must be some maximum value of the static friction. And the actual value of the static friction is going to have to be less than or equal to this maximum value, right? Static friction basically could be anything. It's going to just react to whatever other forces are applied. It's going to be equal and opposite to whatever other forces are applied, forcing the object to stay in place to stop its motion up to this maximum value of the force. And the equation that we have here is, this is a lowercase mu sub s times n. So this here is a mu. Mu here is our coefficient of static friction, and n is the magnitude of the normal force. So if we're looking at how difficult it is to move an object, how big this maximum static friction is that can keep us from moving, it depends on this value of mu, this coefficient, which is a measure of how rough the surfaces are. A rougher surface would have more friction. A smoother, more polished surface would allow an object to slide more easily. And then here we have the magnitude of the normal force, because if you have the two surfaces are being pushed together with a lot of force, if there's a lot of normal force there, then you'll have more friction. If the two surfaces are interacting lightly, you would have less friction as a result. We just said that static friction is a reactive force. It could be any value between 0 and Fs maximum, depending on what other forces are acting in our system. To contrast that, our kinetic friction has a fixed value. Our kinetic friction has a fixed value of mu k times the magnitude of the normal force. And that is true regardless of the speed of the object. So static friction could be any different value if the object's not moving. If the object is moving, then you have kinetic friction. Kinetic friction has a fixed constant amount, regardless of the speed of the object. Kinetic friction always acts against the direction of relative motion. Most of the time what that means is that if you're pushing an object and the object is moving to the right here, then the kinetic friction would be acting against the motion, pushing back to the left. And just like the equation for static friction, kinetic friction depends on the magnitude of the normal force, and mu k, which is this coefficient of static friction, which again is a measure of the roughness of the surfaces, of the surface of the box in this case, and the surface of the floor that they're rubbing against, right? Every pair of two different types of surfaces would have a value of the coefficient of friction that you would get from a table. Technically, there's a third type of friction that exists, and we're going to mention here, but we're not going to consider in problems usually, and that is rolling friction. If you have a tire that's rolling, each point on the tire is stationary relative to the road as it rolls, right? The tire isn't skidding along the road, the tire is rolling, and each point on the tire comes into contact with the road and then breaks that contact as the tire continues to rotate. Technically, there's a small amount of friction associated with that, and there's an equation for rolling friction, but we'll find that our coefficient is so small that we are going to neglect rolling friction. I also wanted to distinguish rolling friction from kinetic friction. A lot of folks think that car tires should have kinetic friction because the car is in motion, but remember that kinetic friction means you are sliding across the surface or skidding. So you can have kinetic friction for a car tire, but that's when you lock up your wheels and you're in a skid or a slide. Typically, the car tires are rotating relative to the ground and rotating at the same speed as the ground going by, and so there would be rolling friction, which we are generally going to neglect. Where friction is coming from is the microscopic interactions between two objects, right? Most objects seem to be smooth, but they are actually rough at the molecular level. You have the bulk of the material where all of the atoms are bound together in whatever way is best for them based on their chemistry. But at the edge of the material, you have a few molecules that don't have the neighbors to bond with the way that the rest want to. And so these at the edge will tend to bond to whoever's available. So if you have two surfaces that are in contact with each other, those surfaces will tend to make these extra bonds from these sort of floating molecules at the surface or at the interface. And so it depends on what the materials are to say how well they bond together. So that is a measure of the coefficient of friction for a given pair of materials. We can also say that stronger bonds are going to form when the surfaces are stationary or not moving, because they have a chance to kind of settle in and form more energetically favorable bonds, which is why our static friction, or at least our maximum static friction, is greater than kinetic friction. Think of if you are trying to hold on to an object and somebody's trying to pull it away from you, you can hold on to it much more strongly than if somebody tries to kind of snag you as you are walking by them. If you have, if somebody just reaches out and tries to grab your arm, it's usually not as strong of a bond because it's just kind of a passing motion. And the same sort of thing here. If these atoms kind of snag on each other as they slide by, it is not as strong a bond as if you have a stationary, two stationary surfaces where they can really settle in and form stronger bonds. We're also going to have more bonds being formed when the surfaces are pushed together more strongly. And so that's why the force of friction depends on the normal force A higher normal force, larger normal force, means that the surfaces are being pushed together, which means you're going to have more points of contact. So you're going to have more bonds, which is going to give you a stronger force of friction. Here's the table that we're going to use that have our coefficients of friction. On quizzes and tests, you'll be given a table, this table or one very much like it. Notice that for each pair of materials, you have a different value of the coefficient, because the coefficient depends on the chemistry, the chemical makeup of those two materials. Notice that you have a different static and kinetic friction for each one. We said that we're ignoring rolling friction because it is 1/1000th of the other values, so we can just ignore it. It's too small to really matter. Notice that the static friction is always bigger, or the coefficient of static friction is always bigger than the coefficient of kinetic friction, because we said that when the two surfaces are static, they have a chance to form stronger bonds than the kinetic case when they're sliding past each other and they're just trying to grab each other as they go by.